Welcome to Brain Vision.
So for problem 15.199, we'll be given for the planetary gear system of the drawing, the angular velocity of gear C, which is 30 radians per second, and the angular velocity of gear D, which is 20 radians per second, both counterclockwise view from the right. And we've been asked to calculate common angular velocity of gears A and B, and the angular velocity of shaft FH. Okay, actually, the whole derivation of the solution is quite long, and I might have to skip some parts. But anyway, let's begin. So the first thing that it has to be made clear is that for gears A and B, there's both a common rotation about the inclined shaft FBA and a common rotation about the shaft FH. It's not only that they rotate about the inclined shaft FBA. Okay, and the calculations would have been easier if the rotation was only about the inclined shaft. But anyway, for that reason, we better use the formulas from the formal definitions you will see later. So let's assume that the common angular velocity for the gears A and B is typically omega vector, which is omega x, omega y, omega z. And just to be clear, this is in terms of the axis system that will be given for description of the problem. Someone might already see a simplification that can be done. Actually, we can take this as 0. Why? Because the shaft FH rotates about the x-axis, and the angular velocity of the gears A and B is on the xy plane momentarily, of course, for the instance shown on the drawing. Then we will impose the following very reasonable conditions. Let me write them down. Which simply say that the linear velocity of point 1 at the rim of gear A equals the linear velocity of point 1 at the rim of gear C. The same for point 2. The linear velocity of point 2 at the rim of the gear B equals the linear velocity of point 2 at the rim of the gear D. This is reasonable. Otherwise, the gears wouldn't move properly with respect to each other. Okay, if we write down the formal definition, the formulas. Omega again is the common angular velocity for gears A and B. R2 equals omega d vector cross product R2. Okay, we have to be careful here. The next step is to write down the position vectors R1 and R2 and do the calculations to see where they lead us. But we have to be careful because in order to use this formula, so we need to take the positions for points 1 and 2 with respect to an origin which belongs to the lines of the axis of rotation for all the gears A, B, C, and D. So I hope it becomes obvious from the drawing that point F is the appropriate choice for our origin. And if we use point F as our origin, then R1 equals minus 80 I hat 60 jihad. This is millimeters. Then R2 vector equals 80 I hat plus 50 J hat. This is again millimeters. And given again the system of axes, let's write down the vector expressed for the angular velocity of gas C and D. I hat radians per second vector omega D equals radians per second. And if someone does the calculations, I'm gonna skip the calculations. Given these values, the linear velocity of 0.1 at the rim of gear A is 260 x component of the common angular velocity 80 y millimeters per second, and I did this using a determiner. It's more convenient. Correspondingly, the linear velocity for point A at the rim of gear C is this one, and also the linear velocity of point 2 at the rim of gear B is this one. And the linear velocity of point 2 at the rim of gear D is 1000 millimeters per second k hat. So we have two equations and two unknowns. The two unknowns are the omega x and omega y, the x component and y component of the common angular velocity. And if someone does the calculations, can get this answer. Radians per second. That was the answer for task A. Let's immediately go to task B. We need the angular velocity of the shaft expressing the common angular velocity. In terms of the angular velocity of the shaft, we can write it this way. Common angular velocity equals the vector sum of the angular velocity of the shaft plus the angular velocity of gas A or B, whatever, it's B, relative to the shaft. Which again, it's exactly the same for gear A. Okay. If we use now what we wrote before, these conditions that we had before, let me begin with this one really quickly. 2 I'm just rewriting what I wrote before using the typical formulas for the linear velocity of points for point 2 and expressing omega using that expression there. And actually taking the angular velocity of the shaft on the other side of the equation, I get an expression like this. And if someone does the same thing for the condition, for the other condition, for point 1, can get a similar expression like this. Okay, what can we do with these two now? I hope it might be immediately apparent that this is a system of two equations with three unknowns, and we need another equation, we need another relation in order to solve the system. We can construct such a relation by taking the magnitude of the above relations, which I hope it is clear that actually it simplifies to expressions of angular velocity, the magnitude of the angular velocity times radius, giving us the linear velocity at the rim of a gear. So if we take the both, let's say, the magnitude of both expressions, we'll get again a quite complicated expressions like this one. This R capital B is the radius of gear B. This is the absolute the angular velocity of gear D and then the angular velocity of the shaft are in the same direction. So we don't need any vectors now. We just need the absolute difference between the magnitudes times R d capital, which is the radius of gear D. The same for gear A. So we have now this nice system. We know that one. We know that one. We can calculate these from the drawing using some trigonometry, which I won't do. I just tell you the results. And we can eliminate these two because they are the same. And if someone does the calculations, eliminate these two and use the fact that A equals to 10 millimeters, and our capital B equals 49.1935 millimeters. Okay, and yeah, solve for omega s. We get finally, I run out of space. The angular velocity of the shaft equal to 25.4917 I hat radians per second. This is final result for task B, and I have to tell you that it it differs a little bit from the suggested solution at the end of the book, but I believe this result is more accurate.